We will continue our discussion on Chapter 6 on electronegativity and polarity, both bond polarity and molecule polarity. First of all, let's talk about electronegativity. This is one of those periodic trends that are very important in chemistry because they determine, or it determines, the polarity of a molecule. Now, there are other factors that are part of that, but electronegativity is the basis of it. So what do we mean when we say electronegativity? Electronegativity is the ability of an atom to attract electrons. So how strongly does an atom of an element attract electrons to itself? Typically, if you remember back, we talked about the periodic trends. We said that some elements have very high ionization energies, and those are found on the right-hand side of the periodic table, and some have very low ionization energies, which are found on the left-hand side of the periodic table as you're looking at it. Those that have low ionization energies so those atoms that have low ionization energies, they lose the electrons very easily, and therefore they're not going to have high electronegativity values. They're not highly electronegative because they don't want those electrons. They're giving them up. So the elements that have the highest electronegativities are going to be found on the right-hand side of the periodic table. And here's the trend. Electronegativity increases as a general rule from left to right in the periodic table and from bottom to top of the periodic table. Once again, if you remember that fluorine has the highest electronegativity value of all, then anything, as a general rule, anything going away from the fluorine, so down a group or from right to left of the fluorine, will decrease in electronegativity. Now, as you can see, this little figure here gives you electronegativity values for all these elements. You can see that it's not a beautiful upward trend, right? There's a little bit of variation here. And when we're going to learn how to do calculations with electronegativity to actually determine for sure whether a bond is polar or not, or whether an element is more electronegative than another. But if electronegativity values are not given to you, just follow the general trend that it increases from left to right in the periodic table and from bottom to top. Obviously, an element that has higher electronegativity value is said to be more electronegative, which means that it wants those electrons more than another atom that has a lower electronegativity value. Here's a sample problem, and I am going to do the first one for you, then you can work on B and C. For each pair of the elements, indicate which one you expect to be the most electronegative. Is it rubidium or lithium for question A? Then you will work on calcium or bromine, phosphorus or chlorine. For doing these types of problems, pull up a periodic table. You can use the electronegativity value table as well, but it's not imperative because these will be given to you sufficiently different enough so that you should be able to determine it just from the general trend and not necessarily from individual values. But if you want to be more precise in your answer, you can use electronegativity values for each of these. But I am just going to use the periodic table. So I'm comparing rubidium to lithium. And here's the periodic table. Where do I find lithium? Here's lithium right here, row number 2. And where do I find rubidium? I find rubidium right underneath it in row number 5. Now I can look the values up, but I also know the general trend that electronegativity values increase as I'm going from the bottom of a group up to the top of the group. So if I'm looking at lithium, lithium is found higher in the group than rubidium, and therefore lithium is going to have a higher electronegativity value than rubidium, because rubidium is found further down the group, and the trend is the electronegativity decreases as you're going from top to bottom. I am going to give you some time to work on B and C, and you can do it either way. You can just use the periodic table, or you can use the actual electronegativity values to determine which one is the most electronegative. Moving on to bond polarity, a bond where two elements are have the same electronegativity value, so they're exactly the same when it comes to electronegativity. They are nonpolar bonds because both of those atoms are pulling the electrons that they're sharing equally towards each other. And so we can talk about 3 different scenarios where we can have a nonpolar bond, meaning that neither one of the atoms is pulling the electrons that they're sharing more towards itself. We can also have the case of a polar bond because the distribution now of those electrons that they're sharing together is not the same on both sides, and that is because one of the atoms is more electronegative than the other. Those are known as polar covalent bonds. We also have the extreme species, which is an ionic species, where those electrons are completely transferred from one to the other. So here's sort of a pictorial of what 3 different types of bonds look like and 3 different types of molecules. If you think about the molecule of chlorine, it's made of 2 chloride atoms or chlorine atoms, and those atoms are sharing 2 electrons between them to form an octet each. Now, if I look to the electronegativity table, I will find that chlorine has a value, I believe it's 3.0 or 3.5. And the point is, both of those chlorines have the same electronegativity value, and therefore, when I'm trying to figure out how much time those electrons that they're sharing are spending around one atom versus another, they're going to be the same. It's similar to playing tug of war, but both teams are pulling the same exact amount, and so that middle is not moving at all because they're being shared equally. That's why this becomes a nonpolar bond, because those electrons are what impart an atom of a negative charge, right? We talked about the electrons carrying a negative charge. Well, if those electrons spend the same amount of time around one chlorine as another, then that means that those negative charges will cancel each other out because they're in opposite directions. They're pointing in an opposite direction. If, however, I have a molecule like HCl, where chlorine now is the more electronegative element, so chlorine is more electronegative than hydrogen, That means that those electrons that they're sharing to form a bond are being drawn more towards chlorine, because that's what electronegativity means. The chlorine wants them more, and so they spend more time around the chlorine than they do hydrogen. That means that that extra electron that the hydrogen is contributing to the bond is now spending more time around the chlorine than around the hydrogen, because chlorine is more electronegative. That means that chlorine is going to gain somewhat of a negative charge because it now has an extra electron that is not its own. It's the hydrogen's electron. And so it gains a little bit of a negative charge. Now, it's not a full negative charge like an ionic species, because we don't have a complete transfer from the hydrogen to the chlorine of that electron. They're still sharing them, but that electron spends a lot more time around the chlorine than it does around the hydrogen. And we can talk about partial charges here. So a partial negative charge on the chlorine, not a full charge because that electron is not completely transferred to the chlorine from the hydrogen. So it's a partial negative charge. And by default, then hydrogen is going to have a partial positive charge because now it's lacking even that one electron that it had. And therefore, if I'm looking at the distribution of an electron density map, where the red shows me the negative charge and the blue shows positive charge, you can see that the negative charge is going to be concentrated on the chlorine side and the positive charge on the hydrogen side. And now we have what is called a dipole formation. Dipole, di meaning two, pole meaning two poles. This is what the separation of charge means. It forms a dipole where I have two charges that are now separated from each other. I have a positive end and a negative end. This means that my bond is polar. It is not nonpolar anymore. When we see the distribution of the electron density in the chlorine molecule, you can see that they're exactly symmetrical. And so they will cancel each other out if we add them up. That's why this molecule is nonpolar. But this one is polar because I have one end that has only blue or mostly blue, and the other end that has mostly red, so that's mostly negative. This is mostly positive. I can also have an example of an ionic bond here. I have sodium and chlorine, sodium ion and the chloride ion. You can see that there's pretty much blue on the sodium part and pretty much red on the chlorine part. So I have almost all my negative charge right here, almost all my positive charge right here, and then a little bit of sharing to bond the sodium to the chlorine. Not a whole lot. So there's electrons that spend some time in between the two, but not a whole lot. This is really a complete transfer from the sodium to the chlorine of that one electron. And that's why I have a total separation of charge and a formation of an ion. Here, I don't have a formation of an ion. They're still sharing that electron. But here, that electron from the sodium has been completely transferred to the chlorine. We can have a continuum, if you will, and we'll talk about that in just a little bit more. So we call these types of bonds here nonpolar bonds. We call these polar covalent bonds. And then these are ionic bonds, ionic species, which are really a form of a polar bond, but an extreme polar bond. So you can see that we have a continuum, right, of the bonds. On one hand, we have the nonpolar bond right here. So molecules like chlorine, fluorine, bromine, they are on the nonpolar end because the electrons are shared equally. On the total end of the spectrum, or the opposite end of the spectrum, we have the ionic bond. On this end, we have a complete transfer of that electron or electrons from one atom to the other, forming ions that form ionic bonds, electrostatic attractions. Here they're sharing, but they're sharing equally. Here they're completely transferring. And then the area in between, we have polar covalent bonds. Starting with slightly polar because the electronegativity difference is similar. So they have similar values. Here, somewhat polar because the electronegativity difference is getting larger. And then on the spectrum, the end of the spectrum closer to the ionic bond, we have very polar molecules. Like water, for example, is a very polar molecule because the electronegativity difference is very large. It's getting close to a complete transfer of electrons. Here's the bond polarity rule of thumb that we're going to use, or 3 rules of thumb that we're going to use. We consider a bond to be ionic if the difference between electronegativity values of the 2 atoms that we're considering is equal to or greater than 2.0. When we do these types of problems, we're going to look at the electronegativity values. So look at the table, and if you do the electronegativity difference, not addition, but difference between the 2 atoms that are involved in the bond, if it is equal to 2 or higher, so greater than 2 or greater, then it is considered an ionic bond. A bond is considered polar if the electronegativity difference is between, so it's at least 0.5 but less than 2.0. So between 0.5 and 1.999. So it's less than 2 but at least 0.5. So you can see how large of a range that is. Now, if it's close to 0.5, that's going to be considered slightly polar. But if it is almost 2 or 1.8 or 1.9, then it is very polar. So those are the 2 ends of the polar covalent spectrum. The bond is considered nonpolar if the difference between those electronegativity values of the atoms is less than 0.5. So between 0 and 0.5 or less. Okay? That would be this end of the spectrum. So this is the rule, the rule that we're going to follow. So 1, 2, 3, we're doing the difference between electronegativity values. And if they have these, so if it's equal to or greater than 2 is ionic. If it's at least 0.5 but less than 2, it's going to be polar covalent. And if it's between 0 and 0.5, then it's going to be considered as nonpolar covalent bond. Classify the following bonds as nonpolar, polar, or ionic. And I'm going to do C for you. The carbon-carbon double bond in C2H4. So in these 2 molecules here, you have a diatomic molecule. So there's only 2 atoms, but here there's more. When we have these types of molecules that they're polyatomic, they have multiple atoms, you will be specified a particular bond. So in this case, I'm looking at a carbon-carbon double bond. If I were to draw the Lewis dot structure of this molecule, I would have a carbon double bonded to another carbon, and each carbon is single bonded to 2 hydrogen atoms. And the question wants me to figure out the carbon double bond, to classify it as nonpolar, polar, or ionic. I could also say the same thing between the bond between carbon and hydrogen. I can classify that bond, the CH, but it's asking for the carbon-carbon instead. So, and it doesn't matter, I just put a single bond here, or a line here, but it's a double bond. I was just following this rule here. But the carbon-carbon bond, which is a double bond in this molecule called ethene, is going to be a nonpolar bond. Why is that? Because I have a carbon bonded to another carbon. If I do the electronegativity difference, I go to the table and I find that carbon has an electronegativity value of 2.5. So this carbon has 2.5, but so does this one. So the difference then is 2.5 minus 2.5, giving me 0. And therefore, if I follow my rule of thumb table, it is a nonpolar covalent bond. If I were to look at the CH bond, carbon has a 2.5 value, electronegativity value. The hydrogen has a 2.1 electronegativity value. So if I did the electronegativity difference for the CH bond, I would do 2.5 minus 2.1, giving me 0.4, and that bond would still be considered nonpolar because it is between 0 and 0.5. Now, follow the same rules to do A and B. In this case, you only have two, so basically both of them are diatomic molecules, so you don't have to worry about multiple atoms. But we do the same thing when we look to specific bonds within a polyatomic molecule. Moving on to electronegativity and molecular polarity. Now, we can have molecules that are polyatomic that can contain polar bonds. So if I'm looking at just the bond between two of the atoms in that molecule, it can be polar, but the molecules themselves are not polar molecules. If I have two equally polar bonds, but they're pointing in opposite directions, the dipole moments will cancel one another. And that tells me that the molecule is nonpolar overall. Now we can do this with molecules that are very simple, or this when we have molecular shapes that are a little more complicated. So let's take a look at CH4, for example. In this little picture here, now it doesn't have to be CH4, but I have a central atom that is bonded to 4 other atoms that are the same. They're exactly the same. Now, if the central atom here is more electronegative than these atoms, then the dipole moment, it's written as an arrow with the head of the arrow pointing towards the more electronegative atom, which would be my central atom. So I have these 4 vectors that are written this way. They're all pointing towards the central atom because it's the more electronegative. Long story, if we were to do the dipole vector sum of these by using mathematics and physics, the sum of all these would equal 0. Why? Because they are equal to each other and they are pointing in a way that will actually cancel when we add those dipole vectors. That is because I have a central atom that is bonded to exactly the same type of atoms around it. What happens if I replace one of these atoms with another atom that is more electronegative than my central atom. Let's say I have chlorine here instead of the hydrogen. So I have carbon, hydrogen, 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 and a chlorine. Well, chlorine is now the more electronegative atom in this bond, the CCl bond. So even though these three are the same, this bond does not have the same bond polarity as those three. You can see it's pointing in the opposite direction because now the chlorine is the more electronegative, and so the arrow is pointing towards the more electronegative atom. Now when I do the sum of these dipole vectors, they do not equal to 0 anymore. And therefore, this becomes a polar molecule, whereas this one is not. Because all of these atoms are the same atoms, whereas here they're not the same. And that will change bond polarities and the sum of the dipole vectors. We can argue this with all of the molecular shapes that we learned previously. So if I have the same types of atoms bonded to my central atom, then those vectors will add up to 0. But if I don't, then they will not, and I have a polar molecule, whereas this one is not polar. So here's kind of how we look at it. If I have equivalent dipoles that are distributed symmetrically, they cancel each other out, and they make the molecule nonpolar. So here's the trigonal planar molecule. We have a central atom bonded to three of the same types of atoms. These dipoles are equivalent and they are symmetrical. That means that their sum is going to equal 0. Now, if I have dipoles that are equivalent, but they are distributed asymmetrically because I replaced one of these with a lone pair or two lone pairs. Now, even though these two are symmetrical dipoles, are equivalent dipoles, they're not symmetrical anymore because now I have replaced that third one from this molecule, the third atom, I've replaced it with a lone pair that makes these two asymmetrical. And that means that I have a polar molecule. That's the difference. So if I have a molecule that is symmetrical because it has the same types of atoms, then I have a nonpolar molecule. But if I replace one of those atoms with a different one that has a different electronegativity value that makes my dipoles not be equivalent, or if I replace it altogether with a lone pair, then I have asymmetric dipoles and I have polar molecules. So what makes the dipole asymmetric? Two things. If I substitute one of the atoms with a different atom that has a different electronegativity value, or if I replace an atom with a lone pair, that also makes my dipoles asymmetric and will make the molecule polar. Now, the molecule can be slightly polar or very polar, depending on what the electronegativity values will be for the bonds. But if I do one of these things, so replace an atom with a different one, so take this one and replace it with another atom, for example, that has a different electronegativity value than these two, then I have asymmetric or not equivalent dipoles. Or if I replace the atom with a lone pair, like I've done here, or I've done here, I took this atom and I replaced it with a lone pair. Now I have non-asymmetric or asymmetric dipoles, which makes the molecule polar, versus this one, which has all of the same atoms and no lone pairs. So this is nonpolar. If I were to take this and replace it with a different atom that has a different electronegativity value than the other three atoms, then this will make it a polar molecule. Let's look at this sample problem. Determine whether the following molecules are polar: BCl3, AsCl3, CHCl3. I will do this one for you. the first thing that you need to do is to draw the Lewis dot structure for these molecules. And then you're going to figure out what shape you have. So you're going to figure out whether you have a tetrahedral shape. So that I'm talking about the molecule here, not just the electron group geometry, but the molecular geometry. So what's the shape of the molecule? And you're going to determine whether you have the same type of terminal atoms bonded to the central atom, whether you have lone pairs or not, or whether you have replaced one of the atoms with a different atom that has a different electronegativity value, because that will make the molecule polar. So let's look at CHCl3. If I were to do all of those, so draw the Lewis dot structure for CCH3, I would get something like this. Now, don't worry about the wedge and the dash. This just means that this bond here is pointing away from me, and this is pointing towards me in three-dimensional space. But this is what it would look like. So I would have the chlorines bonded to the carbon and the hydrogen bonded to the carbon. Now, the shape of this molecule would be tetrahedral because I have 4 electron groups around the central carbon. 1, 2, 3, 4 electron groups. That gives me an electron group geometry of tetrahedral. I also have 1, 2, 3, 4 atoms bonded to the said central atom, which makes my molecular geometry to be tetrahedral as well. So now that I know the shape of the molecule, I have to determine whether it is polar. 2 things are going to make my molecule polar. One, have I replaced, so out of my electron groups, have I replaced one of those atoms with a lone pair? Okay, well, no, I don't have a lone pair on my carbon. I have 4 atoms that are bonded to it, but no lone pairs. There are 4 single bonds. Now, they could be double bonds or triple bonds. It doesn't matter. But in this particular case, I have single bonds and 4 single bonds and 4 atoms. What is my other case that would make, so the change that I can make to make my molecule polar? Well, I can have one of the atoms that is bonded to the central atom. I can take that and replace it with a different one. So you can see I have 3 chlorine atoms bonded to the carbon and 1 hydrogen atom. So this hydrogen atom is different than the other 3, which makes the bond polarity between the carbon and the hydrogen different than the bond polarity between the carbon and these chlorines. Because this is a different bond polarity, if I do the dipole vector addition, the sum of all of these dipoles is going to be different. And therefore, this molecule is actually polar. Now I'm going to give you some time to try A and B. Remember to start with the Lewis dot structure. Make sure you've got the correct structure. Determine the shape of the molecule, and then determine whether you have a lone pair that will make it polar or a different atom than the rest bonded to the central atom, which would also make it polar.